Welcome to the MIT Mobile Forum. Today, I'm glad to have Drago Anguelov from Waymo join us to talk about the technology stack behind the Waymo autonomous driver. Drago is the leader of autonomous vehicle industry. You serve about 250,000 trips per week now. You recently announced the highway operation in the Bay Area of this. So first of all, tell the audience a little about yourself. How did you get into this field?
So I'm a vice president of engineering at Waymo. I used to lead what was called the applied research team at Waymo. And now the team evolved into a new entity called AI Foundations. We build some of the large foundation models for driving off-board typically, where you can use more compute and to leverage less constraints on latency and the response. So we can analyze a lot of our data and serve as a teacher to the onboard models or the simulator. So that's what my team does. We still do a lot of research. You can see some of our past research is on waymo.com/research. We have over probably 100 publications by now. We've been doing this for a while. Generally, Waymo is Alphabet's autonomous driving company. It has a long history. I did my PhD at Stanford, and there I overlapped with Sebastian Thrun, who from Stanley fame, for those that know the first DARPA Grand Challenge in 2005. And Sebastian made it to Google and was at some of the roots of starting Waymo. And I was around there actually, so I had exposure to autonomous driving for a long time, both from my PhD and through my early work at Google, which was not on Waymo. It was on various computer vision perception models. I worked on Street View. I worked on understanding photos and annotating them for Google Photos and other applications. So we shipped a lot of the backends using neural nets for the large image understanding models at Google. And for a while, I stayed out of the autonomous vehicle space. So the first maybe 10 years of my exposure, I stayed away and felt it's not ready to really ship and scale. I felt our understanding, especially of perception and our capabilities in AI were limited for this. And then around late 2015, I decided to get into the space. So I've been at Waymo over 8 years. Generally, I view myself as a machine learning AI modeling person, also as an engineer. And I think Waymo on its own end has a long history. So it started in 2009, which is over 15 years ago. We had our first autonomous drive of a customer, of a person in 2015 in Austin, Texas. We opened our fully autonomous service to Phoenix East Valley in 2020. And since then, we've been expanding quite rapidly and growing capabilities. So now we're in 5 major metros, serving, as Jinhua mentioned, over 250,000 trips a week to customers, paying customers. And these 5 metros now are the whole San Francisco Bay Area, which is the west side, but that's what usually is called the area. Phoenix Metro, Dallas, sorry, not Dallas, Austin, Atlanta. And so we're in Los Angeles, last but not least. These are the 5 big metros we're in. We announced freeway driving to customers. We've been actually doing in small amounts this for a long time. We've been working on freeway driving. And as of very recently, the last few weeks, we started actually driving external folks on freeways. We announced we are starting driverless service in 5 more cities this year, which Miami being the first. And in coming weeks, we announced we will do also Orlando from Florida. And now we're getting to Dallas, Houston, and San Antonio. And for 26, we've announced more cities. So we're scaling to at least 12 cities and internationally. London comes to mind. We announced we plan to start fully driverless operation in London next year. And we're also on the ground in Tokyo with some of our vehicles as well, experimenting there. So we've entered the stage of scaling our service and letting many millions of people at this point experience it in more and more cities and more conditions, which is called from suburban to dense urban with San Francisco, which is probably the second densest city in the United States, to highways now, to potentially snow. We announced we will do Detroit, San Diego. We are expanding our operational design domain and trying to really cover the full space of needs that are needed for autonomous driving.
This is a stunning success you have achieved, but why did it take so long? We had this dream in, let's say, 2007. We said we'll solve this problem in 5 years. The AV industry as a whole somehow underestimated the challenges. Where do we underestimated? What was the challenge that until now we couldn't solve?
I think a lot of this now is becoming obvious with other AI models too. So it's not hard to give very compelling demos. You can do it fairly quickly. Maybe in a year or two, you can have compelling demos. Actually, in 2010, there was a challenge, I believe, by the founders of Google for the self-driving car project to drive, if I remember correctly, at least 10, 100-mile paths in routes in California without disengagement each. And they did do it then. That was 2010. My first ride at Waymo vehicle was in 2012 on the freeway. So there's been a lot of rides experienced and demos given. But I think what is the challenge with this technology is you need to have a high level of trust, and you need to be able to handle a really wide variety of cases to put them at scale into the world. And you need to handle it without safety problems, without accidents that can really injure people. And handling such a wide range of things, I don't think people appreciate it. What I call how long the long tail is.
Yeah.
And the long tail extends to two parts. So when I talk about autonomous vehicles, there is the first challenge is build a driver that can ideally handle them. And I think this now a lot of people do. And in L2, for example, you can put out a driver that mostly drives most cases now, one way or the other. But to have L4, you also need to convince yourself that you believe this driver actually is safe. And building it and convincing it yourself it is safe at scale are both very formidable challenges and both take a good amount of time. So for L4, you need to master both. So when you combine all of these things, it does take some time. That's it. Waymo over time mastered a solution to both, and we've been able to iterate and scale and make improvements at a fairly quick pace at this point, which of course then you can observe in our expansion rate. And we've also been able to build a stack that we do believe rises quite well from one city and one area to another. And again, that's another prerequisite that you need to have if you need to scale at the rates that we are now pushing to do.
Now we finally tackle this highway driving part. What was the challenge that we couldn't deploy at scale, and what are the solutions?
So there is a bit of this initial belief when I was getting into autonomous driving that maybe freeways are easier. And why is that? Because actually freeways, most of the time, nothing particularly interesting happens. You can go behind in some lane and drive in it for a while and exit, and everything is quite straightforward to handle. But now you say, okay, downtown San Francisco, there is all kinds of crowds and strange behaviors and complex intersections. However, freeways present a qualitatively different challenge. And the main challenge comes from the speed at which you're driving. And so still a lot of complicated things can happen on freeways. There can be collisions in front of you. There can be all kinds of weather effects. There can be construction. People and animals still can come out. There can be all kinds of debris. Even if things happen on freeway quite rarely, particularly interesting or challenging things, they do happen. Comes in millions of miles. And you're operating at a very high speed. And some of the things can be hardware failure. So your brakes, power steering can go off, brakes, some of them can go in. You can have all of these things that for you to be safe, you need to think through your stack bottom up. Compute failure can happen, all of this. So you need to have a robust safety case spanning all the way from the hardware and the system to the software and the validation. And often one of the underappreciated challenges of freeway is that if something happens, you can't necessarily just stop. When you're at 70 miles per hour, it's not like you hit the brakes and stop in the middle of the freeway. That's already not safe. So the requirement in the city, in San Francisco, worst case, maybe you can stop and you mostly are moving at 10 miles an hour and it can be okay. In the freeway, you cannot do that. So you need to keep driving often, potentially for a mile until you hit the shoulder. Even in degraded condition, all of this needs to be tested and validated. And so between the rare events and the additional system-wide safety requirements, it can take a while. That said, we've been working on it steadily for many years. And I think we believe at the point where we can start rolling it out to the public, which it is a big milestone. A lot of people at Waymo are quite excited. They've been working on it for a while.
Now you open in the Bay Area. Presumably you will open in the Phoenix very soon as well. You even have a bigger ODD. It's even more useful to have the highway driving.
I believe, I don't know exactly, actually, the rate of which exactly areas we're opening at what cadence. The intent is to open freeway driving in most of our metros. Indeed, in the larger the metro is, and the more you're doing airport drop-offs and so on, the more incentivized you are to offer freeway riding. Yes, indeed, from one end of our Phoenix area to the other, it can be over an hour, and on the freeway, it can be 3 times shorter. Most people would not want to sit in a car as nice as it is for too long. And so it's key to making progress and making our service useful. Now, separately, I did not announce this, but we also, as part of our opening freeways push, we're also enabling rides to San Jose Airport in the Bay Area, which is, again, our second airport or third that we're already servicing. And it's a key use case to take people to these transportation hubs like airports. And I hope we will be able to do more of this, but freeway is another enabler to this for us.
So there's a constant debate between this end-to-end design, architecture design versus modular design. Yesterday during our conversation, you said we will take a more practical approach. So you choose to take a handful of these major modules, still come independent, and you inject the end-to-end at a certain point. Give us a picture of how your strategy is in integrated two thinking here.
So I don't think it's a dichotomy. It's like either you're end-to-end or you're modular. There are different concepts. Each serves certain uses. So end-to-end is the ability to train from outputs to inputs and learn rich representations automatically of the environment from these inputs. And it's quite powerful. So instead of the humans designing some representations, intermediate representations, you enable the system to do it. And I think this is now standard and for a while. And a lot of the, say, visual language models and a lot of the AI models do this. And that's part of the appeal. So end-to-end is very useful for this capability. And I think also because in our domain, we do have a lot of data of driving. So there is a lot of gradient to push from outputs observed by human drivers and what our people should be doing. So it's appealing. End-to-end is a good property. But there's this question when people turn it into a dichotomy, is it end-to-end or modular? End-to-end by itself is not necessarily enough. Can our experience tell us that one can do better by not just relying on just pure end-to-end learning? And I'll give you just a simple example why. So the input space in our domain is extremely high dimensional or complex. Situations occur and develop over a period of 10 to 30 seconds. That's a lot of temporal context you potentially need to understand. And then in our case, we have 1 or 2 dozen cameras on the car. We have half a dozen lidars, half a dozen radars. This is hundreds of millions of readings at 10 to 30 hertz. So you end up in the billions to tens of billions of readings per second. Now, from all of these representations, you need to learn to predict XY trajectory or like an action, which is throttle or steering. There are multiple numbers. How much gradient can you push? So it's a lot of data. But now the question is, and a lot of these large models just trained like this, you need to be able to do reasoning. You need to understand ideally, and you need to not having rich representations of the environment help with this. And they also help with understanding, hey, these are the cases when the model even is doing well or not. If it's just a black box, it's problematic. And so to combine these things, so some kind of structured end-to-end potentially addresses both concerns. So I can say this. So it's not a either or. I think from a practical approach, you use each technique for what it is useful for.
Particularly in this safety critical application, you need the controllability, you need the fixability on this. You need to introspect the model.
Yes, and the model needs to potentially be able to introspect its own understanding as well. So having richer representation often helps with this.
The next question is the integration with the foundation model. Like, for example, you guys are already using Gemini into this. Give us the trade-off being between using the existing foundational model, then add on top of this driving specific one, versus, say, training autonomous vehicle driving specific model from scratch.
And I'll say a couple of things. One is, so I'm not claiming we use or don't use Gemini, just to be clear. We have not announced anything specific. That said, we have research into both kinds of models. So we have our own, a lot of bespoke Waymo architecture and developments over a long time now, over 10 years. So there's a lot of interesting learnings in model design for autonomous vehicles. We may get more into this in the future. So we have Waymo bespoke learnings how to do models. We also have a lot of experience, and we have paper, for example, called Emma, which was exploring the use of Gemini for autonomous driving tasks. And that has a certain set of appeal as well. But one of the learnings also of that paper is that probably Gemini or by itself is not the best thing you can do purely to drive. You need a lot more of also Waymo specific learnings added to this to really handle better spatial reasoning, multimodal inputs, and longer context memory. All of these things you can enhance further from just using a vanilla Gemini 1.0 model at the time, which was the paper. We have an experience with both. One of the big appeals of these vision language models is that, of course, now we understand, and I think we've understood it for a while, but now recently, as the models got more powerful and the architectures, the scaling laws become even more compelling. And this idea of pre-training on internet scale knowledge and then fine-tuning to specific tasks is very appealing. This world knowledge of vision language models, for example, derived from the whole internet, both as language and as image, is appealing. And we want that. We don't want to necessarily observe every single situation ourselves. If I can transform world knowledge, it's appealing. Now, recently, there's been this other very interesting trend called world modeling. And this is causal or acausal video prediction. Particularly interesting for us is the causal variant of this. So for those of you that follow some of the generative AI modeling, there was a really interesting model called Genie 3 by DeepMind. And that's a world model. World model learns to essentially dream future video of and potentially create future video of scenes with controls, which can be language or potentially even steering controls. They could move with the keyboard and steer some kind of virtual bicyclist in some environment. So these world models also capture interesting knowledge from video. The visual temporal knowledge, that's also very interesting. So bringing these capabilities into our stack are very appealing. That said, for us, because we're fusing multiple rich sensors, including 3D, and we want rich spatial understanding, a lot of these adaptations require a little bit of way more special sauce to truly land in the best possible way. So we combine the two.
When we talk about this vision model, they typically is camera based, like a 2D vision.
That's right.
But in AV, we drive in the 3D real physical world. Okay, I'm using LiDAR on this, right? So what's the distinct challenge in incorporating the 3D data?
So we have certain investigation into this. Historically, what was learned, and this was a long time ago, even maybe you can say 10 years ago or more, is that when you're, especially if using multiple sensors in the environment, but even if you just do a camera-based perception over time, if you want to reason about spatial concepts, it helps to represent some of the world in what we call bird's eye view. So there Euclidean coordinates centered around the vehicle into some kind of grid, or whether 2D or 3D, into which you collect a set of features, or you have anchor embeddings with which you query a bunch of sensors, somehow mapping things to 3D and fusing a lot of information there, as opposed to thinking of having, I don't know, a couple of dozen separate sensors, each with its own representation, seems to generalize a lot better. So if you are able to reconstruct Euclidean representations of the world, you can reason a lot better. You can model things a lot better. You can power simulation that's physically realistic a lot better. So a lot of the vision language models, at least in their straightforward current representation as learned from the internet, do not directly model or are concerned about this Euclidean 3D space. And so now there's an interesting challenge because they're not trained to necessarily reason in that space, and you want to preserve the world knowledge. It's tricky to adapt those models too much or fuse them into that space without potentially destroying some of the world knowledge. So there's some interesting considerations. Depending how you design it, you need to be mindful of. Ideally, you want to do more spatial reasoning and Euclidean space reasoning, but depending on how the model is trained, you may need to make certain trade-offs. And we're trying to understand these trade-offs. But generally for us, when you have all these sensors and you're doing spatial reasoning, being more 3D is helpful. Now we have this paper, I think you were asking to me earlier when we were talking about, we have certain investigation into how one can try to uplift a set of representations, so embeddings learned in 2D, such like when a VLM like Pali, that's one of the early Google VLMs, one of the first actually in general in the space. And so we have certain papers where we study how we can effectively uplift a 2D learned representation to 3D.
The recent paper has this enhancing motion forecasting with plug and play and MMM on this. So you preserve the generalist capability of MMM, but plug in. So tell us a bit detail about this one.
For grammar is an example of a study where we try to uplift a VLM model to 3D space without losing too much of the initial representations, and showing that when you train then end to end through this updated representation, you may have better scaling towards predicting future trajectories or driving commands. That's one thing we did.
Yep.
I think some of this plug and play is a different take. So we're showing how to extract more structured representation from these VLMs. And sometimes you need to query them in a closer format to textual format, and then leverage the outputs of that and combine it with some autonomous driving specific representations jointly and predict. So there's different ways to mix more autonomous driving traditional approaches and VLMs, and these are some of the example papers.
So in this scaling law paper, you talk about the distinction between the scaling law in the motion space versus scaling law in the language space here. Helps a little bit understand. He said the optimal AV model approximately 50 times smaller than the optimal language model. What does it mean?
So just to recap what we did in this paper, we have an approach called Motion LM that we developed maybe 3 years ago or more. And the idea there was, hey, can we take the large language model idea of an autoregressive decoder model, and how next open prediction in language you pre-train and fine-tune to generate conversations? What treat motion prediction in a scene as a conversation? So the idea there is you have a set of actors in the world, and they're all speaking to each other simultaneously by moving. It's a very intuitive idea. It's trying to apply the LLM concept to autonomous driving model. And when you do this, essentially everyone's outputting tokens simultaneously at each other. And you can model these joint streams of tokens that ultimately model the interactions between all of these agents. Formulate this architecture, turns out it's quite compelling, and you can train it with, of course, next token prediction over arbitrarily long horizons that you may want in these scenes. And then you can apply them to forecasting. So why is forecasting important of agents? I think just to ground people here, autonomous vehicle domain is the first, at least I worked in, and one of the first in robotics, where you really have these safety critical interactions that are multi-agent interactions. So a lot of the challenges we're solving is not hitting certain pole near the road or an static object in front of us. A lot of them require complex negotiation and interactions with human agents and other agents, whether they're drivers, pedestrians, bicyclists, and so on. And so you have this multi-agent interaction. And furthermore, you need to model it in a simulator typically, because once you start playing a scenario that was interesting and you start doing different behaviors, the agent needs to respond to you. So the behavior depends on your behavior. So if you want to play out the scene and understand what happens, you need some kind of bespoke modeling of agents too, not just yourself. Then you have a world model that predicts possible futures. And this model is that kind of simplified world model where you're just modeling how agents in environments behave when they interact with each other. So I have this model, and it encodes a representation of the world and tokenizes, gives it as an input to a LLM-like model, and you output these motions. Now the question is, how good is this model? That was quite state-of-the-art for motion prediction when we did it. And then we studied what happens if you keep scaling this model. So because one of the great this autonomous vehicles have two great properties as a domain, as a robot. One of them is the hardware, I would argue, is ready as a product. So we have the sensors and compute we need, I believe, at this point to deploy autonomous driving vehicles. Second is we have a ton of demonstration of one behavior often the humans, even experts in driving, we get to observe not just our own drivers that drive our cars. Sometimes we have drivers driving our cars. They can teach us how to do it. You also observe other humans driving the cars too around. So there is no shortage of demonstration. Most robotics domains, other than autonomous vehicles, don't have these two necessarily yet in the amount we have. So it's really appealing. Now, we have this multi-agent problem and safety, a whole bunch of challenges ourselves, but this is at least a wind at our back. So now in these models, because we have all this data, you can say how much does it generalize and how well does it scale? And there are two interesting differences between LLMs, at least, and the models we experiment, these motion conversation models. One of them is, so the motion vocabulary is small. Language is extremely rich. The amount of tokens and concepts in language can be in the hundreds of thousands, and I don't know, even more if you count all the languages and so on. In motion, you can only do a few things, so the vocabulary is a lot more limited. The challenge for us is all the richness of the inputs. And then you need to think of these joint futures. So our output space is simpler, and so maybe you don't need such a big decoder to model so many possible outputs. That's one. Second thing we see is it's all relative to how much data. So also our data is less diverse potentially. If you just drive, a lot of the driving is boring. So the scaling laws are affected by this as well. So that's why your model ends up being smaller for comparable amounts of data. First of all, because our long tail is quite long. You're looking at unusual interactions happening, for example. They don't happen that often. And furthermore, our output space is simpler. So some of these things, I don't truly have a definitive answer why the scaling laws are a bit different, but there's some really good properties of the scaling laws also in this paper for this architecture. So traditionally in robotics, there's this question, if you train a model to imitate with, say, next token prediction, with teacher force, for those that understand this concept. The question is, okay, so you train it what's called open loop. You feed it some input, you have it dream some possible interactions. Each step at a time, you can teach a force and train it. And that's called open loop. Does it apply in closed loop? Meaning closed loop means you're running, so you learn some behavior model. It's some kind of action policy. It takes in observations of the world and takes action step by step. And typically for us, the challenge is for us to understand how well a driver is doing. It needs to drive on its own policy for a while, and then you look at the outcomes. You need it in a simulator with all these agents that also, of course, have their own policies that are chosen suitably to test the driver and be realistic. And actually, it's an alarming topic. And so now, where was I going with this? Yeah, so you're doing this closed loop rollout. Now, if you train in open loop, the question is, do the model translate the gains in closed loop? In closed loop, there's an additional problem. It's called covariate shift. To accumulate errors in your predictions. You can increasingly get out of domain for the model, and then the machine learning model can do worse and diverge and potentially start behaving suboptimally. So one of the interesting things we were studying is it actually differs by architecture. So different architectures and formulations, open loop often does not translate to closed loop performance. If you improve open loop, there is a bunch of papers and studies on this, and closed loop can get worse. For this model, what we found is one of the good properties is actually open loop improvements translate to closed loop improvements. This is not a given, but it's really good result. It's a good property of this specific model, and that's one of the things we showed.
There's also cross-agent skill transfer. That's also really interesting benefit from that. Yeah.
Yes, you of course can. There is an interesting question when you study. It's like, how many agents do you want to embody when you're training? How many agents do you benefit? If you want to learn a good planner, how does modeling of other agents help you learn a better planner is also interesting.
Right.
So it's a fascinating area. I think there's more such studies to be done with the current other alternative models for doing this, like diffusion. I look forward to people doing more. Maybe we will do some.
You mentioned this is social interaction between multiple agents. The challenge autonomous vehicle had is the interaction with the first responders during special cases on this. That indeed requires some degree of social intelligence. So where we are in terms of the state of art in the understanding each other's gestures, intents, positions, all those.
So we have been continually working on this. And I think our capabilities in this have been improving. Even in the past, before too much of this generative AI technology and large models kept developing, we have blog posts, for example, from maybe 5 years ago or so. We would actually model the pose of the pedestrians near us and the gaze would understand. So you can see we have a blog post showing you how the skeleton of all these pedestrians moves, and you can see Waymo understanding it. We have examples, of course. We have to do our best at understanding gestures of personnel that's directing traffic, of responders, of firefighters, and we work on this. It's challenging in construction cases. Of course, people also can give you all kinds of instructions, including holding signs. All of this we work on. And I would like to believe we're continuously improving in this. It's not a simple problem. This is situational awareness of humans.
Yeah. On that, I think the autonomous will need to understand the kind of the hierarchy skill. There's a different set of rules, but under certain condition, you have to violate certain rules. For example, you may have a landmarking, but under construction, you may have a cones. On top of the cones, you may have people holding a sign, and against the sign, people may give you a gesture. All of them may come to each other. If you need to understand which one is more important and follow which type of rules in that condition.
I agree. I think there is an interesting question of, can you write the reward with a single formula? What's the reward for autonomous driving? I think it's a bit like this. Each rubric or type of rule, in theory by itself, it's relatively easy to specify. You shouldn't cross a double yellow, and you shouldn't, follow the stop sign if a random person's holding it. You should obey the stop sign if it's on the proper sign on the sign. There's a bunch of these rules you can outline, but when you mix it all, then it becomes a case of we need to prefer some over others. And I think this kind of information and training the models to do that is important. So when possible, a lot of these imitations and potentially simulations that we do to test and to train the models do help with this. So one can target aim to learn and collect information, both from our expert drivers and also in other ways from rewards, from outcomes in simulators to keep shining light on this. It's not a simple problem. It's not easy to write down a single reward function.
Moving to this long tail and alternate data set, Waymo made a big effort of popularizing this open data set and invite for challenges, WOD. Tell us a bit more about the data set. Are you keep updating that, enrich the data set? What type of challenges you are inviting people to participate?
We've been working on this since 2019 and we released it in 2020, and we continue expanding it and enriching it with what we believe is either useful data or useful task definitions and metrics and leaderboards that help community make progress on tasks and challenges that we believe are important. So every year we try to expand the set of things we have provided, and it spans a very rich set of cases. It spans all kinds of perception challenges, typically at the intersection of camera and LiDAR, and 3D, which is more autonomous vehicle specific. And it spans a lot of behavior and challenges, agent modeling, forecasting of future interactions. Just now, very recently, we had a very commonly requested feature. So if you want to do planning, typically you condition the policy on some route that you want the agent to take because you're usually trying to get to a certain place and the route tells you where you're trying to go. We had not published the routes and now we're publishing them. So they're available. So it will be planning like challenges. So planning challenges will be easier to do with data we provided. But this was our way. So the Waymo Open Dataset, the way we treated it is it's a way to connect to the community and give back in the form of, hey, these are the challenges and the tasks that we believe are relevant to work on. And here is data we believe is suitable for the community to also make progress with us on these challenges. And here are the metrics we believe are reasonable to measure what is progress. So I believe that's one of the best investments we could do to collaborate with the academic community. And we will continue doing this. I think most recently we launched an interesting challenge that's called End-to-End Driving Challenge. That was interesting too. There is a lot of interest in end-to-end modeling and reasoning in these systems and handling rare cases. So we collected several thousand fairly rare types of situations we see on the road, and we annotated it, and we're testing if models built by the community can generalize and understand these more rare types of situations that are less about bounding boxes and agents moving in 3D space. They can include complex semantic understanding. And so there's been a lot of uptake of this challenge, which was good to see.
When your team published these research papers, what's the process does it take to translate into the actual production in the Waymo driver on this? It's already developed at this stage of technology. So let me give you two options. Which one is a more priority? One is saying the technology, of course, will continue to improve, but it's good enough. Let's push it to 100 more deployment. So I move from build to bring to everybody, right? Make it more affordable. Versus saying, we'll continue push the safety frontier from a 5x improvement to 100x improvement, which means maybe more costly, but much more safer in that.
Yeah, so in terms of research, we're an applied research team historically, and now we build also these large foundation models for Waymo. It's more of a direct mandate. So with our research, we always try to investigate areas that we thought would move the bar in Waymo's understanding or capabilities. So there was always a strong intent and push for folks when they develop a particular concept or advance in research to try and experiment directly with the production models and stacks and see how these advances translate to production impact at Waymo. So we really emphasize this part. I can't one by one describe which of these works really impacted production versus didn't, but it was always meant to shine light on key areas we felt it's important to make progress in or increase our understanding of. In terms of should we just do more safety? Should we expand more? You always want to do both. You want to push the bar in multiple directions. I will just tell folks a fact where we are with regards to safety in our understanding. So Waymo is we explicitly try to be transparent about our performance in the domains we drive and engage with the cities and file the reports with the necessary details. And one of the things we have continued doing, even from early on, we periodically publish our safety statistics from fully autonomous driving in the cities where we do. And every few 10 million miles that we drive, we update these statistics. And the last report was maybe a couple months ago to a bit longer. It was close to 100 million miles mark. So we are over 100 million fully autonomous miles driven mark. We are over it. But around that time, we published the reports of how we're doing. And the short is, in our estimate, compared to human drivers in the same operational design domains where we go, we are at least 5 times safer with regards to collisions and injuries. And we are at least 12 times safer with regards to impact on pedestrians and bicyclists than comparable human drivers. So that, I believe, at 100 million miles, data is starting to become quite statistically significant. It's good evidence that these vehicles contribute to safety. And as I'm not sure most people know, I think a few of you do since you're in the domain, annually 40,000 people in the United States get killed in accidents. And so increasing safety of driving is a big factor. And I believe autonomous vehicles have a key role to play, but we need to, of course, follow and scrutinize and report how actually we do in these domains as Waymo tries to do. Now, separately, of course, and I started this conversation, we're trying to scale. We want to bring this technology that we believe at this point is quite good to a large number of people. And from some point of view, this safety numbers is an additional mandate to try to do that. We want to bring these capabilities. And so to me, as a machine learning person, a lot of the interesting research is how do we harness even better the reasoning capabilities, the scaling capabilities of the models, such that with the data we have, we can build drivers that generalize a lot better to more new conditions and build simulators and testing harness around these drivers that can tell us a lot faster, validate them in new conditions. So as long as we can make progress in that and cover the operational design domain, such that snow, like we want to do snow, Detroit, where we're going has snow. We want to do left side of the road driving in London and Tokyo. We want to do freeway at a lot larger scale than today. That will, over time, increase in volume. We're starting somewhat on the small side, but all of these things we want to push. Of course, we don't want to compromise safety. I personally believe, and I hope our safety numbers keep improving in the future further. There is good reasons to believe it's possible.
Thank you so much, Drago. We had an extremely active chat. We had close to 400 people joining this call.
Let's try a few.
Let's go for a couple. So look, very early on. So just for context, we had Missy Cummings join this forum a couple weeks ago. So I'm sure you're familiar with some of her views on the topic. Early on, Eric Sabina asked a question: does Waymo still have some quote unquote minders monitoring autonomous vehicles to help them get out of a jam from time to time? So the question is about teleoperations and backup humans. Missy had made the point that autonomous vehicles are not really autonomous because there's still some human support. So the question for you is really, Douglas Milliken asked, he's particularly curious about Missy's comments on latency and high-speed driving for human backup drivers in this kind of command center or this backup center.
So I would say that we have teleoperations support, but our vehicles primarily and the vast majority of the time are fully autonomous. And this operation support for us does not drive the vehicle at any time. So it may advise the vehicle in particularly rare situations that are unusual and may give it a guidance under which the vehicle can decide to drive a certain way from usually a stopped position. But we do not rely on people taking over and driving vehicles in real time. As you said, especially in high speed situations, this is very challenging. And all this freeway driving, I don't believe it's easy to do because you need quick reactions. We're really trying to be as maximally autonomous as possible.
Is it fair to say that you would foresee the role of these teleoperations centers declining moving forward into the future?
I believe so. We already handle the vast majority of cases fully autonomously, and we do not have these people drive the cars at Waymo. They don't drive the car directly.
Okay. There was a whole set of questions about the operational design domain. Sal Tannenbaum asked, how hard is it to adapt the system to move the operation from one city to another or from one country to another? Sal asked, what magnitude of software modification is required when moving from drive on the right to drive on the left? Barbara Brega had a similar question. Any further comments on how you guys are thinking about this new diversity of the operational design domain?
So I think with the recent models, we see positive transfer between different types of vehicles and between different domains. And so the fact that we believe we will be driving London next year autonomously, I think should be some sign of the fact that we believe that there's significant positive transfer from right side to left side. I can say that. Generally, this is more and more the case. And I think when you have a big broad base of examples, I think every new domain needs less and less. Also, I think the more different a domain is, the more examples you need, but it's still the common base that we're collecting. I think it's a great platform that on top of which you need a lot less bespoke local details.
When you mentioned airports, a few people jumped in. So Robin Chase and said, airports, this makes me wonder, how does an AV respond to, say, a police officer directing traffic in real time? Stanley Young mentioned it's a very dynamic environment with the curb, with construction, maintenance. Any sort of views on the unique challenge of a Waymo operating through a chaotic airport scene?
It is chaotic. It varies. Sometimes also vehicles have specific areas they go and park, but indeed, generally dropping off people and the picking up can be very chaotic. We see a lot of chaotic environment in the city cars we drive in the first place. I would not say that the airport is particularly drastically different than things we already have.
Okay, fair enough. There was a question about why the expansions are mostly in southern states.
That's because they don't have snow. And
Yeah.
we don't have to think and validate. And for one more challenging case before we have to. That said, snow is a matter of time. We want to launch a few cities. We are carving up the ODD, the full ODD in parts. So first you did suburban, then we did dense urban, then we are doing freeway. We of course did a bunch of weathers, fog, rain. We do even storms. We often drive up to fairly extreme precipitation. It's just, it's nice to handle problems one at a time.
Sure.
And so we're getting to snow, but a lot of cities that have snow for a long time, it's easier not to do it at first. And so that's what we did.
We were very excited here in Boston to see a number of Waymo vehicles on our roads, mapping and testing and so forth. And we certainly do have snow. So I hope that's a sign that Waymo is soon on their way to New England.
By the way, we've been working with snow for years. So if you look at also blog posts and so on, we send vehicles and collect and experiment in snowy conditions from Lake Tahoe to Minnesota and so on. It just, when you do deployments, you may want to take your time on some longer than others. So we have not completely ignored snow. I think it's an important condition. It's just working towards it over time.
Thank you so much for giving us this 1 hour to share, pushing the frontier of this AV technology. Also, as someone from academia, thank you for sharing the Waymo open dataset so that the whole community can engage with this. Everybody, please join me. Thank you, Drago.
Thank you guys so much for having me and for the thoughtful and interesting questions.